All right, welcome guys, welcome back. In this video now, we're going to be looking at work, energy, and power, and we're just going to be trying some past papers on this question. And somewhere along the way, we will remind ourselves of some of the theory stuff that we actually need in order to approach some of these questions. So what I'm gonna do now is I've got this question here. Okay, but just to do a little bit of a reminder on the concept of work, energy, and power. Okay, so the work, energy, and power part, web as stated, we've got the work part, and one thing that we know about work is that work is essentially identified or given per se by the formula W is equals to F delta X cos of theta. Okay, but to actually really get the definition of what work is, we'll sort of disregard the cos and we'll just have this. Okay, so work is essentially just the product of a an object's force acting upon it and its displacement, basically. Okay, and work is similar to energy. So with it being similar to energy, we'll actually give it the very same SI unit as energy, which is just J. And this is what is known as the work energy theorem, which says that the work done on an object is equals to the object's change in kinetic energy. And as much as kinetic energy is measured in joules, then so is work. Work is also then measured in joules, like so. Okay, with that in mind, let's take a look at some of the questions. Okay, just a quick reminder. Remember, this represents the force that is acting. Okay, the one which we are actually putting into focus when we're calculating our work. Okay, and then our delta x is the displacement. And then remember, the cos here is not that cos, but it's actually the theta. The theta is not actually this theta per se, but it's actually the theta, which is the angle between the displacement and the force that is within focus or within question in this case. Okay, so let me just get rid of this and let's tackle some of those questions. Okay, so we get rid of these bad boys. Okay, so have them go. Okay, like so. Okay, let's take a look at the questions now. Yeah. I think we need to do this and then can we put it back to focus. All right, so let me grab my pen there. Okay, so it said the diagram below shows a crate of mass 50 kilograms, obviously it's given there, sliding down a steep slope. The slope makes an angle of 30 degrees with the horizontal. The motion of the crate as it moves down the slope is controlled by the worker using a rope. Okay, so there's actually some tension. So we have a worker that's pulling upwards, okay, and pulling with a force of 300 newtons. And a constant frictional force, which is down there, a constant frictional force of 50 newtons x on the basically on the crate as it slides down. Okay, so we've got this, some dude is pulling up with a rope, hence tension, and then there's friction that's actually making it slide down the slope there. Okay, all right, so let's see. We're told to draw a free body diagram, okay, and give it some labels. And note how the mark allocation is 3 there, so we're actually expecting 3 forces to be acting on this object. Yeah, okay, so let's get the analogy down. So here we've got this 50 kilograms crate, and it's on the horizontal, that makes an angle of 30 degrees. The motion of the crate as it moves down the slope is controlled by worker. Okay, so we actually have the worker here pulling down on it. Yeah, it's controlled by the worker pulling down on the slope, and there's some tension and so on and so forth, and the frictional force is there as it slides down. So this object is actually sliding down the slope, so we actually have FG parallel actually supporting the motion here because it's actually going down the slope. So we actually have friction going in the other direction. So if we're looking at that first question there, like so, to draw that free body diagram, we'll have our dot there, and there's a force that's already provided, which is our dear friend tension. So we have tension. Okay, like so. And then we have friction because this object is moving down the slope, so we won't have friction here, but we'll actually have our friction here. So we actually have our FF right there. Okay, and then going down the slope like so, that's where we shall have our FG parallel, which is responsible of taking this crate down the slope. Yeah, so easy. Okay, then for the next one, they're saying state the work energy theorem in words. I'm not going to stress this one much because I believe that you guys have had a whole lot of experience with the guidelines, so you should know that the work done on an object is equal to the object's rate of change in kinetic energy. I cannot stress myself much on that. Okay, now with that third question there, it says the change in kinetic energy of the crate is 450 joules as it slides from the top to the bottom of the slope. So we know the change in kinetic energy, which means our delta EK is actually provided to us as 450 joules. Okay, which actually means that the W net is 450 joules based on the work energy theorem, isn't it? Which means the rate of change in kinetic energy is the same as the net work done on the object, as the definition says. Okay, what are we supposed to calculate here? Use the work energy theorem to calculate the length of the slope. Okay, that works. I think we can work around that. So we know that W net is equals to delta E. Okay, this is what we know, and essentially we're looking for delta X. So that's going to be somewhat of a long calculation. Okay, so let's look at this crate. Okay, what are the forces that are actually doing work on this object? The forces that are doing work on this object is actually these ones. We're going to now disregard things such as the FG, perpendicular, and the normal force. They're not doing anything here. In fact, they're canceling each other out. So when we're looking at the W net of this object, we're actually going to disregard those forces. Okay. So when I'm actually expanding my W net, I'm going to say this. When it comes to my W net, we have WFG. Okay. WFG parallel is doing some work on the object, plus, because remember net means I'm actually summing up all those works, and then I've got W of FT, isn't it, for the tension. Yeah, and then I've got plus, right, I've got W F, I can say friction, which is that bad boy right there. Okay, and then we've got other forces at work here. We'll actually have to think about our dear friend the normal force here. Yeah, we can talk about the normal force here. I'm running out of space, so I'm just gonna proceed on the spot. Okay, and all in all, this is essentially equals to, well, delta EK. Okay, I know I've got a very horrible handwriting, but you're gonna have to bear with me on this. It's pretty terrible, honestly. Anyways, let's begin to expand our FG there. So our FG, remember, work is F. Okay, let me just write that down aside. So work is F delta X cos theta, right? I'm going to expand this for each and every work that I have there. So for my FG here, my force that is actually acting on the object here, oops, the force in this case, the F, is actually 50 in it. That's actually provided to us. Let's actually double check that. Okay, yeah, it is given there as 50 newtons. Okay, yeah, okay, that's, in fact, I think I've substituted for frictional force there or something like that. Yeah, but yeah, okay, so we've got 50 there. Okay, in fact, no, I'm missing something. Oh yes, my FG, my FG, I don't know what the F is. That's actually a good analogy to keep in mind. I don't know what the F is, but I know that FG parallel is the same as MG, right? Is the same as MG, basically, yeah, which is just the mass. Okay, so I'm going to say that's 50 multiplied by 9, comma 8. Okay, and I still have the delta X and cos theta from the work formula, yeah. Okay, this is what I'm essentially trying to solve for, basically. In fact, I think I might as well just substitute for my theta. Okay, we may just substitute for theta. So let me just propose I do that. Okay, so we're sitting at what was the angle between that friction and, okay, the angle between friction and displacement. The angle between friction and the displacement here is actually sitting at 0 degrees, yeah. Okay, because it's actually having its displacement here, and the friction is actually there. I mean, the FG is actually there, isn't it? So the displacement, it's actually being displaced in this direction, and the FG is actually there, and the angle between those two is actually at 0 degrees. Okay, proceeding plus. Okay, now we're doing it for our dear friend tension in it. So for tension, we're still sitting at 50 by 9,8, yeah. Delta x still and cos, but this time my theta is sitting at 180 degrees. Reason it's 180 degrees is obviously because of the angle between the displacement and tension. It's sitting at 180 degrees. If you actually take a look at it here, our tension is here, but our displacement is here, and the angle between that is sitting at 180 degrees. Okay, plus, and then we move on. Okay, so we just did tension and now friction. Okay, so I think we're given the value of friction here in it. Okay, actually I think I just did friction. Yeah, I just did friction now. Okay, I'm actually supposed to be, okay, let me do the tension now. I think I just did friction. Yeah, let me do the tension now. The tension is given as 300 newtons, so this is just going to be a good 300 delta x cos, and the angle here is sitting at 180 degrees. Okay, and this is all equal to 450, isn't it? Because this is the energy that was provided there. So we've got 1, 2, and 3. Okay, you'll be like, why didn't you the Fn? Remember, it's not doing work here. I honestly don't know why I even wrote it down to begin with, but nonetheless. Okay, so what I'm now going to do is propose that I take delta x out as a common factor, because it seems to appear there, there and there. So I can take delta x out. It's actually a common factor. This is, I mean, basic math. So I'm going to take delta x out, and if I do, then let's see what remains. Here we've got 50 multiplied by 9,8, is it? Okay, and the cos there, I think the cost was sitting at 60 or something like that. Anyway, so we've got 245, yeah, minus, and then here we take delta x out, we're going to be left with 50, and then here we take delta x out, we're going to be left with 300, is it? I'm basically taking angles out here at this point, yeah. Okay, we close it off, and this is all equal to, this time we'll have 150. I've also divided the cos's out, hence I've got 150 there. Okay, and this will leave me with a delta x of 4,29 meters. Okay, that was more of an easy solve of some sort. Okay, let's look at the other question that we have there. Calculate the coefficient of kinetic friction of the crate as it moves down the slope. So the coefficient of kinetic friction. This one shouldn't be easy, shouldn't be that hard, because one thing that we know for a fact is we only have like one formula that has to do with coefficients of friction, which they said coefficient of kinetic friction here. So I'm going to propose this as Fk, which is equal to mu k n, yeah. Okay, then let's substitute what we have. Our mu k is, well, what we're looking for, isn't it? Our friction, we're actually given this as 50, isn't it? That was 50 newtons, yeah. And then the n part, our normal force now is actually going to be sitting at, if I expand this part, it's actually mg cos theta, because we're at an angle, isn't it? Where theta is the 30 degrees that we're given there. So then this part, if I substitute it, we just have 50, yeah, which is the mass of the object, and then 9,8 is my gravitational acceleration, and then I've got cosine of 30, and then we close that off. Okay, and then you do the whole solve, which I'm not going to bother going too much into detail. You're going to end up with a mu k of 0.12. And remember, this does not have SI units, coefficient does not have SI units. Okay, and I believe that is the last question for this past paper. Okay, if we take the next question that I have here, I have this one, question 5, which says a 3 kilogram metal block moves from rest at a point A, so it's moving from there at point A down an incline, so it's going down the incline like so, as shown in the diagram below, and reaches a speed of 6 meters per hour, or 6 meters per second, sorry, when it reaches point B. Okay, section A, B are both frictionless. Okay, so this is frictionless, and I'm guessing we have friction there. I see kind of like a ragged drawing of some sort there. Okay, anyways, would you describe the movement of the block on section AB as a free fall? Yes. Why? Well, it's frictionless there, isn't it? Yeah, it's frictionless, and it was moving from rest as shown. Yeah, so the only force that is actually acting here is gravity. So to answer that question, yeah, that's a yes, because we only have gravity. Of course, you should like answer this question in full, but because of the sake of time, I'm not going to write the whole thing in full. I mean, you guys know what I'm talking about, innit? Okay. Number 2, calculate the net work done on the block as it moves down section A, B of the path. Okay, as it moves down that section A, from A to B. Okay, the net work done. Okay, so the net work done can be calculated in either two ways. You can calculate your F net and then do the whole thing, but here we don't have any forces here. Okay, but one thing, I am given a velocity here, and one formula that has something to do with velocity is the W net is equals to delta EK, because I know that EK is a half mv squared. We've got a little v there that we can play around with, so that should give us what we need. And if I expand my delta EK there, I would realize that, okay, delta EK, remember delta EK, whenever you see a delta, this just means the EK of final minus the EK of initial. Yeah, if we look at the final stuff, when it reached that point, we have a certain half mv squared for it. In this case, it's final, minus a half mvi squared. Yeah, this is basically what I'm expanding. Yeah? A half, and then the m, well guys, the m is obviously a mass. I mean, come on, like really, this is just a 3 in it. Yeah, that's 3 kilograms. It's actually provided there. Okay, what about the Vf squared now? Well, the Vf squared is the velocity, the final velocity. When it reached point B, it was said to be 6. So that's just a good 6 there, minus. Obviously, when it was at rest at this point, it had no kinetic energy. It had high potential energy, but low kinetic energy, hence 0. Why 0? I mean, come on. Eventually, its initial velocity is 0, which makes the whole thing 0. So we should probably be good at that point, yeah? Okay, so then all in all, if we punch that into the calculator, we'll end up with 54 joules as our W net for that question. Yeah. Okay, I think that answers that part. Yeah. Then okay, the next question. Okay, let me just erase this this part. So I'm just gonna get rid of it. Okay. Yeah. Okay, yeah, okay, so grab the pen again and let's grab that third question there. So that's question number 3. Okay, so for that question we asked to calculate the height of the block at position B. So it's sort of they're asking for this height, for that height. Yeah, so when it comes to the height, I'm pretty much guessing this has to do this. Okay, let's actually look at it from this perspective right now. Yeah, if you look at it from this perspective, this has not much to do with changing in terms of the x per se. So we're not actually much changing here, we're actually changing in terms of y, isn't it? So if I use my W net, I'll propose, if I use my W net, right, my W net is equals to delta K, isn't it? Yeah, and my W net, if I start looking at all the forces that are doing some work on this object, it's only gravity, isn't it, at that point, isn't it? Yeah, I only have gravity doing work on this object. Only after it passes through point B that's when we begin having other forces such as friction. But now it's at point B. So at point B, when it's having the specific height, the only force acting on that object is gravity. So this is the only force that I'm going to include within my W net. Okay, and remember W net is F delta X cos theta. So I'm just going to go into sort of a direct substitution here. Yeah, so it's, remember, W is F delta X cos theta in it. So what is the F for this point? Remember, we're talking about gravity, isn't it? So I can almost say this is Fg, of which Fg is the same thing as mg in it. So I'm going to say my mg in this case, well, mg is mass, so I'm going to substitute in. This is a 3 kilogram object, and then my g is 9,8, like so. Okay, and then what is the delta y? Well, the delta y is unknown because that's actually what I'm calculating. And what is cos? Okay, the cos is actually 0 degrees because this object is now moving down, isn't it? And gravity is also acting on it downwards, and really the angle between there is sitting at 0 degrees. So my cos is 0. Yeah, and then my delta ek, I can make substitutions for this delta ek. Let me just get rid of this now. Okay, so for my delta ek, remember W net is delta ek, hence I'm working with that. So my delta ek, actually I know how much delta ek is in it. Yeah, let's scroll up a bit. Yeah, okay, so my delta ek, delta ek is the change in kinetic energy, isn't it? If we take a look at it at this point, I think this is like a calculation that we've already done per se. Yeah, that is sitting at oh, it's half mv squared. It's something that we've already done, sort of like there. We still have that 54, so I might as well just put in the 54 because that's the energy at that point in it. So I might as well just put it there. So we're sitting at 54 here. Okay, then it's a matter of just performing those calculations now. So let me propose that I grab my calculator. Okay, so there's the calculator. I'm not sure if it's actually visible. It's in view now. Yeah, okay, I think it's visible right now. So this is what I'm gonna propose we do for this calculation. We're gonna say 3 multiplied by the 9,8. Yeah, so that's just 3 multiplied by 9,8, and this gives us a good stable 29,4. Yeah, so a good stable 29,4. So I'm just gonna write that one down. So that's 29,4 delta y cos 0 is equals to 54. So I might as well divide both sides by 29,4 cos 0, right? So if I do that, both sides, my y, let's do that. Let's bring our dear friend the calculator back into focus. Okay, so now I'm dividing both sides. So I've got a good 54 on the other side, so I'm gonna say 54 divided by 29,4 multiplied by the cos 0, although I know what cos 0 is, but I mean, I can't be too careful, isn't it? And then we get the answer of 0.18 something. I'm not sure if this is correct or something like that. Okay, this doesn't look anywhere near trustworthy. Hang on a second. Let me just double check my kinetic energy. So I've got a half, and then our value of m is sitting at, oh, it's 3, and my v squared, the velocity there was said to be 6, so I'm gonna square that and close it off. Okay, that is a stable 54, and then we divide that by let me see if I have this right. Then I'll divide, oops, do I still have the answer there? Okay, yes, good. So I have my answer and divide it by, I'm basically dividing it by 3 by 9,8, and dividing it by 3 by 9,8 gives me a stable, okay, that's 1,84. Yeah, that's 1,84. Okay, we good. Okay, let me get rid of it now. Right, yeah. So we're sitting with a delta y of 1,84. Yeah. Okay. Oops. Okay, there we go. Let's scroll that down. So my delta y is 1,84 meters. Okay, let's see if we actually answer that question fully. I mean, they said calculate the height of the block at that point. We said it's a 1,84. Okay, however, that doesn't finish that question. Yeah, we have to then take the whole 6 meters, because what we just found now is a difference in a y, isn't it? How much has it traveled? We don't know the height above the ground when it reaches point B, so we need to take this full 6 and subtract this 1,84 that we have to actually find the height above the ground that it's at. Yeah, so meaning our height, we'll call it h per se, is going to be the 6 meters, which is the height that it began at, minus the height that it actually consumed through time, and this is going to be 1,84 that we just got, and we get an h of let me grab my dear friend the calculator again. We'll let him do the work. Okay, and let's see, so we'll say the 6 minus the 1,84 and see what we get. I got 4 comma something, yeah, 4,16. Okay, so we're good. Yeah, so we have 4,16 for that question. So 4, oops, oh Jesus, 4,16 meters. Beautiful, isn't it? Okay, then for the next question, I think there was like a number 4 there. On reaching point B, the block continues to move down to section BC of the part which is said to be 5 meters in length. The block now experiences a frictional force and reaches point C at the speed of 2 meters per second. Use the principle of conservation of energy to calculate the magnitude of the frictional force acting on the block as it moves from B to C. Okay, so now we actually need the frictional force. So I'm going to propose I use the work energy theorem for this. They said use work energy principle, so any of them can apply there. So that's now number 4. Okay. So I always go to this formula because it seems to always do the work for me. Yeah, if we expand this, yeah, so if we look at this object at point B where it was, so remember we had the whole slope like so, at point B where the block now is, yeah, if we look at all the forces that are actually doing some work there, that are going to now begin doing some work, is going to be our dear friend friction, yeah, plus I believe we also have like gravitational force, which is still pulling it down. Okay, I believe that's all that is. There's no applied force or anything else. If we look at things like normal force and FG perpendicular, those are cancelling each other out, so we don't need to worry about it. So it's pretty much only these two forces. So if we actually look at it like this, we've got friction trying to pull it back, and we've got FG trying to pull it down the slope. Yeah. So that's basically what we have, and this is equals to delta EK. Yeah, and then our delta EK. Okay, so now we're actually looking at the kinetic energy here being the initial now, and our final being this part. Yeah, so I'm going to propose that's a half mvf squared minus a half mvi squared, like so. Okay, and then now let's make the substitution. So we know that, let's keep in mind that w is equals to f delta x cos theta, like so. Okay, I'm just gonna make the substitutions as I go. So let's look at friction, for instance, now. So friction is f delta x cos theta, but we don't know the f, isn't it? In fact, we're supposed to be calculating the f, so I'm gonna leave it as is. Do I know the delta x? Yes, I was actually told that the displacement, it actually traveled for a good 5 meters, so I'm going to have my delta x be 5 meters there. Okay, and then this is going to be, of course, cos, and then the theta. Remember, this thing, we're looking at friction now. Friction is there, and this thing is being displaced there, and the angle between there is a good 180 degrees. Okay, plus, and then now let's look at gravity now. So gravity, the gravity, remember, it's like this, isn't it? Now the force of gravity is unknown in this case, isn't it? but now I actually know that the FG in this case is just a good old MG, isn't it? Yeah. So I'm going to then say that part is going to be a good 3 multiplied by a good 9,8. Okay. Um, and then what am I missing here? Yeah. And then we have a cos blah 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 blah, isn't it? Yeah. So this is mess mg, and then we need the displacement. Yeah. And how much is the displacement in this case? Yeah. So we said the height in this case was a good 4,16 at point B. So if we look up at point B here, it was that amount, but the displacement now to actually get to this point would be that good old 4,16 minus this one would be your full displacement. Okay, so we're looking at only this part. So the 4,16, we need to minus this one. It will give us the height which it has traveled at that point. Yeah, so that's sort of like mid-slate that we're doing there. Okay, so that's 4,16 minus that 1 meter in it, and then cos theta part of it now, and the theta in this case is 0 degrees because the displacement is actually going down and the friction is there, so that's a good 0 degrees. Okay, and this is equal to, now I feel like I'm sort of running out of space, so let me sort of draw it back and right there. Okay, so we have a half, and the mass of the object once again is said to be 3, and then the final velocity, remember it reached at 2 meters per second. Let's just double check that. Okay, yeah, then it's given at point C, it's given to be 2 meters per second, so we're good for that one. Yeah, so our final velocity in that case is 2 meters per second, and we still need to remember to square that. Yeah, minus a half. Okay, and then mass, well, it's still 3, and what's the initial velocity? Remember at point B it was said to be 6, and we square it out. Notice how the only unknown in that case is only our different friction here. We're beautiful. So if you complete this entire solve, which I'm not going to stress too much on working on, we're going to end up with a friction of approximately 28,18 newtons. Smiley face. Beautiful. Yeah, that felt incredibly long. So that is that for the work, energy, and power question. Of course, I do recommend that along the way while you look at this video, it helps that you before looking at the solutions, you just try out the question first. In your case, try the question first before looking at how I work through the solution after. Okay, so good luck guys, I'll see you in the next one.